SN14 is about perpendicular bisectors. 14.1 introduces the perpendicular bisector theorem, and then 14.2 will be the converse of that theorem. So starting up at the top with some new vocab, if a segment bisector intersects a line segment at a right angle, then it's called a perpendicular bisector. And just as a reminder, a bisector is something that cuts another object into two congruent halves. So this says if a segment bisector intersects a line segment, so in each of the three graphs below, we have a line segment A, B. And then we have some sort of segment bisector, and a segment bisector can look, it could be a line, it could be a ray, it could be another segment, but we have a segment bisector that is bisecting that line segment AB and is creating a right angle. So like in the first case, line M is intersecting segment AB and creating a right angle. In the second one, it's a ray that's bisecting segment AB and creating a right angle. And then in the third case, it's another line segment, ST, that's intersecting or bisecting segment AB and creating a right angle as well. So it's just like a special type of bisector. So it's a bisector that is cutting a segment in half and creating a perpendicular creating a right angle while doing so. So we call it a perpendicular bisector. Because that's what perpendicular lines are. They're like two lines that intersect and create right angles. Okay, so moving on to the perpendicular bisector theorem. So if a point is on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So equidistant means like equal distance. So if you're not sure of that word, you can leave a note for yourself, equal distance is what equidistant means. It's just kind of like I don't know, it's kind of a shorter way of writing it, but they mean the same thing. So I just want to kind of dissect what that theorem is saying now. So it says if a point is on the perpendicular bisector of a segment, so going back to one of our perpendicular bisectors, it doesn't matter which one, we'll just find a point on there. So let's say it could be point S, it doesn't have to be, it could be any point on that bisector. I'm going to go ahead and just use point S because it's already on there. So if a point is on a perpendicular bisector, which that is, then the point is equidistant from the endpoints of the segment. So the endpoints of the segment are referring to the line segment that is being bisected, in this case AB. So the endpoints would be A and B. So any point on the perpendicular bisector should be and is equidistant from point A and point B. So that theorem says that those two little like dash diagonal lines I just drew, those are the same exact distance and they always will be for perpendicular bisectors. Another just like quick example, I'm going to use the first graph. So our endpoints A and B, if I pick any point on line M, let's say I pick a point right here, that point should be equidistant, that's kind of curved, that point should be equidistant from point A and point B, both endpoints of the segment that got bisected. Okay, so moving down to the proof, this was kind of a long one, so I am just going to kind of uncover the work and explain it. If you're comfortable just taking a screenshot for this one, I think that's okay, but just make sure you're following along. So given that line T is a perpendicular bisector of segment AB, so you can see like line T is the blue one that cuts through, is a perpendicular bisector of segment AB, which is that bottom, kind of like the base of the triangle. We want to prove that AS, or the distance between A and S, is equal to the distance between S and B. So we want to prove that this distance is the same thing as this distance. Basically, like those two like other sides of the triangle are the same length. Okay, so we know proofs always start with stating what is given to us. So we're given that line T is a perpendicular bisector of segment AB. So that'll be our statement number one. Line T is perpendicular bisector of segment AB. The reason is that it was given to us. And then the next thing we're going to do is we're just going to state where it bisects AB, where it intersects AB in general. So the bisector line T intersects AB at point D. This is where it crosses it. So that's our next statement. Line T intersects segment AB at point D, or at D, and then our reason, it's nothing fancy. It's if two lines intersect, then their intersection is exactly 1 point. So if you take two lines and they intersect each other, there's going to be one intersection point. In this case, that intersection point is at D. Okay, so the third one, the third statement we're going to use is that line T bisects segment AB at D. So we know that T bisects AB. We know that T intersects segment AB at D. So now we can say we're like kind of pulling these two together. So T is a perpendicular bisector. T intersects segment AB at D. Grouping those two together to say that line T bisects segment AD at D. So it kind of pairs those two together. And that's what a perpendicular bisector is. Like, it's a bisector, it bisects something. So we would use the definition of a perpendicular bisector for a third reason. Okay, moving down to number 4. Now that we've used like kind of the first three to go ahead and like state, prove, show that line T is a bisector, we know what a bisector does. It cuts a segment in half. So if line T is like cutting AB in half, it's cutting it into two congruent parts. There's AD and DB, and those are congruent because that's what a bisector does. So for 4, we can say that segment AD is congruent to segment DB because that's what a bisector does. So we say definition of a bisector, or bisect, sorry. Okay, so for number 5 now. So we've established that they're congruent. We also have a way of establishing that we know what this angle is and also this angle. So now we can start working on that. So because it's a perpendicular bisector, that was given to us. Because it was given to us, we can state that we know what those angles are. So next we can say, okay, angle SDB is a right angle. So SDB, it's SDB. So it's that right angle that's already even labeled on the graph. We know that because we know there's a perpendicular bisector, and we know perpendicular bisectors create right angles. That's by definition. So reason is definition of a perpendicular bisector. Because we know that one angle is a right angle, we technically know all the other angles around it are also. So like this side, this side, this side, those would all be right angles. So I don't need the two bottom sides, but next I can state that, SDA is a right angle as well. And there's a couple of different reasons that you could write for this, but the next one would be angle SDA is a right angle. Technically, you could use definition of a perpendicular bisector there as well, but if you wanted to do something different, you could use if two lines are perpendicular, then the intersection forms 4 right angles. So that's what we were talking about, where this is also a right angle. This is also a right angle, so they're all right angles. And then moving down to number 7. So if we're saying between 5 and 6, we've said that they're both right angles. So if they're both right angles, that means it's safe for us to say that they're congruent to each other. So we'd say angle SDA is congruent to angle SDB. That's what right angles are. There's a theorem that says that all right angles are congruent to each other. It's called the right angle theorem because they're all 90 degrees, right? So if they're all 90 degrees, they're congruent to each other. And then now we're starting to get to the point where we have some sides that are corresponding and congruent. We have some angles that are corresponding and congruent. So looking back at what we know from the graphic, so we know that AD and DB, those are congruent to each other. We know that SDB and SDA, those are congruent to each other because they're both right angles. So we have a like set of corresponding sides that are congruent and set of corresponding angles that are congruent. If I can prove that a third side, not a third side, but a second side that encloses that angle within it is congruent, then I'll be able to use a congruence theorem to say that the triangles are congruent, and then I can find any side or any angle, or not really any angle, I guess, but any side of the triangle at least, or prove that they are congruent to each other. Okay, so that side that's in pink now, that's the third side of each, I keep saying third side. That's the second side of each triangle. So we have like side and then the included angle, and then we have the second side. So that's on the other side of the included angle. It's obviously the same like length, it's the same line segment. We just have to say that in like our geometry terminology. So the way that we do that is we say that segment DS is congruent to segment DS. Remember, that's like the property where anything is congruent to itself, where you're like kind of looking in a mirror. So it's the reflexive property of congruence. So that one that like feels so silly to have to state, where you're just saying something is congruent to itself, that's the reflexive property of congruence. And then that's enough information to say that the two triangles are congruent. So going back to the graphic, I know I keep writing on here and then erasing it. So we have these two sides that are congruent. We have this angle and this angle that are congruent, and then I have this side that is essentially congruent to itself, but that's the last pair that we needed, like pair of corresponding parts that we needed to show that the triangle is congruent. So now we can say, okay, triangle ADS is congruent to triangle BDS. We just have to think about what property we need to use. So we have a side, an angle, and a side. And that's congruent to a side, that angle, and then that third side again. I keep saying third, sorry, and then that side again. But if it's a side with an angle in the middle and then another side, I think I keep saying third because it's like 3 letters, but there's an angle, it's not a third side. So if we have side, angle, side with the angle in the middle, that's our congruence theorem. Is side, angle, side, SAS, and that order matters. With the A in the middle is telling you that your angle should be in between the two sides that you know from the triangle. Okay, so now because we've said that like the two triangles are congruent, we already know that like, you know, these two sides are congruent, these are like that side is congruent to itself. If the triangles are congruent, then every set of corresponding parts are congruent to each other. So that means that this third side, now I can say third, is congruent to this third side. So AS is congruent to SB. Because no matter what, like if we've proved that the triangles are congruent, we know they're the exact same size. So we can say all the parts are this congruent to each other. So for number 10, segment AS is congruent to segment SB. So what we just drew with like the 3 tick marks. The reasoning is corresponding parts of congruent triangles are congruent. So as soon as we've proved triangle congruence, then we can say all of their corresponding parts are congruent. And then if we're saying segment AS is congruent to segment SB, our goal is to eventually get to like this exact statement, and that statement, like without the segment line above it, that is the distance between A and S is equal to the distance between S and B. But if they're congruent to each other, like their segments are congruent, then we can say their distance is the same. That's what congruence is. So that's the last little part. Number 11 is the distance between A and S is equal to the distance between S and B. And the reasoning or the justification is that's the definition of congruent segments. So right here, we show that the segments are congruent. Congruent segments have the same length or the same distance between the endpoints. So now we're able to say that the distance between those 2 points is equal because we know they're congruent. The reason that we like the distance part is important to get to as opposed to just saying that the segments are congruent is because that's what the perpendicular bisector theorem is all about. So it says that No, up here. If a point is on a perpendicular bisector of a segment, then the point is equidistant, the same distance. So we're trying to get to that distant part of it. Okay, so next example, this is the last one for 14.1. So right here, and again, like the proof, if you don't write the whole proof down, that's okay. I would just maybe screenshot it, save it for later, tuck it in somewhere, add it to your favorites, do whatever you need to do. Okay, so example in the following figure, segment NR is a perpendicular bisector of MP. So let's see, NR is this one, and then MP is this one. So NR is a perpendicular bisector of MP. And then now moving down right here, it says if the distance between N and P is 6, so I'm going to pop a little 6 right here. And the distance between M and R is 2.9, so MR is 2.9. What is the distance, or sorry, what is the length of segment NM? So NM is right here. And we have enough information to answer that because of that theorem right here. So the perpendicular bisector theorem, I'm not going to read it out loud again, but we have a point, N, that is on the perpendicular bisector. That means that that point, N, is going to be equidistant from the two endpoints of the segment that was bisected. So that means that NP is the same length as NM. So if NP is 6, then NM is also 6. So we say NM, segment NM is 6. Okay, so moving on to 14.2, very similar, just reverse order. This is the converse. So 14.2, converse of the perpendicular bisector theorem. Remember that a converse just essentially takes a theorem and switches the order of the hypothesis and the conclusion. So I'm going to go back up to the perpendicular bisector theorem really quick. Okay, so and see, if a point is on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So remember, a lot of these statements, they have, let's see, if and then our like hypothesis would be the point is on the perpendicular bisector of the segment. That's the initial setup. And then the conclusion is that the point is equidistant from the endpoints of the segment. We got to switch those. So that means that for the converse, the what's in purple right now, that's the conclusion that would come first. And then what's in green right now, that's the hypothesis. That's where we would finish. So we just switch the order and try to color code it the same way. Because why not? Okay, so the converse of the perpendicular bisector theorem. I already forgot how I was supposed to color code it. I'm sorry, I have a bad memory. So our original conclusion was in purple, and then our original hypothesis was in green. I'm mostly saying that out loud for me. Okay, so we have if and then in our statement. And then if a point is equidistant from the endpoints of the segment, that was originally our conclusion. It is now bumped to the front, kind of like a hypothesis. That's what a converse does. Then the point is on the perpendicular bisector of the segment. That was originally like our kind of hypothesis. Our setup was the point being on the perpendicular bisector of the segment. This just switches the order. So it was, if P then Q, and now it's if Q, then P. So if a point is equidistant from the endpoints of a segment, then the point is on the perpendicular bisector of the segment. So we can use that to answer this example on the right. In the figure, AB is, the distance between A and B is 7.4 units. That's labeled for us right here. The distance between B and C is 7.4 units. And then the measure of angle A is 65.4 degrees right in here. It's labeled for us as well. And segment AD is congruent to segment CD. So that's labeled for us also. So everything that was given to us is also labeled on the graphic. And then we want to find what is the measure of angle BDA. So BDA is right here, B, and then D in the middle, and then A. So we're looking for this angle right here. And I know it looks like a right angle, but we can't just be like, hey, it looks like a right angle, so it is a right angle. We have to kind of be able to prove it because it's geometry. We got to prove things. Okay, so going back to the converse, it says if a point is equidistant from the endpoints of a segment. So we have a point here, B, and then we have the endpoints of the segment, which are A and C. So we know that the distance between those is equal because they're both 7.4. Says then the point is on a perpendicular bisector. So because we know this distance is 7.4 and this distance is also 7.4, that means that this is in fact a perpendicular bisector. So it bisects and creates that right angle. So that means that both of these would be right angles. And that's enough information to be able to confirm that the measure of angle BDA is 90 degrees. But you just have to be able to show that it is a perpendicular bisector because you know that these two distances are equal.